Hello everyone, welcome to our group presentation for code SEMM2613 Material Science. We are students from the School of Professional and Continuing Education, UTM Space, under the guidance of our lecturer Dr. Nur Akmal binti Fadil. Today, we are diving into the fascinating world of non-ferrous alloy and specifically focusing on the versatile combination of zinc and copper, and more commonly known as bus. So, today representing our group are Muhammad Ehsan, Muhammad Hanafi, Muhammad Hazmi, Muhammad Haziq Shamin, and me myself, Bibi Shubhashini, and also Nurul Atika. In this video, we will explore the solidification process, microstructure, and phase transformation of zinc and copper. So, without wasting the time, so let's move into the video.
Assalamualaikum. My name Muhammad Hassan bin Basaruddin. So my matrix number SX 241667 EMMHF01. So today my slide about grinding metal. So contain 95% copper and 5% zinc. So for grinding metal, which is a high copper alloy, consisting of 95% copper and 5% zinc. So because the zinc content is quite low, it stay well within the solubility limit of copper. If you look at the cooling curve, you will notice it is not a flat line during freezing. So between 1065 degrees Celsius and 1050 degrees Celsius, you will see a slope change rather than a thermal arrest. So this represent the freezing range where then drag of the alpha to solid solution are growing, which in the melt. So by the time we reach 100 degrees Celsius, the metal is entirely solid and consists of 100% alpha phase. So in the micrograph on the right, you can see large equate grind, equate grains. So the characteristics straight parallel lines, you see underlying twins, indicating the material has undergone heat treatment to relieve internal stress. So we will continue with another slide. So this one about commercial browns. So the content is 90% of copper and 10% of zinc. So commercial browns which contain 10% zinc, despite the name, this is a brass alloy. So the solidification process here is a very similar to the grinding metal, but with a slightly wider freezing range. It begin to solidify at approximately around 1055 degrees Celsius and finish at 1020 degrees Celsius. So one thing to note with this higher zinc content is the risk of coolings, where the chemical composition is not uniform across the grain. Though this is easily corrected through annealing. So at room temperature 20 degrees Celsius, the alloy remains a single phase alpha structure. So the zinc atom tuck neatly into the FCC copper lattice. So looking at the microstructure, we will see those same polygonal grain and annealing twins, which are typical for this type of FCC solid solution alloy after they been processed.
Is Mama Hanafi. Okay, this is a jewelry bronze. It contains 87.5% of copper and 12.5% of zinc. We use this mostly for jewelry. Why? Because the high amount of copper gives it beautiful golden color. It looks just like expensive gold, but it is much cheaper. In the microstructure, if you look at the microscope image, you will see clean structures. Scientifically, we call this a single-phase alpha structure. This just means that the zinc has mixed perfectly in the copper. You see those straight parallel lines inside the grains? Those are called annealing twins. These lines are proof that the metal has been heated to make it soft. Because it is so soft, we can bend it into complex shape for necklace or earring without it breaking. Now let's move on to page 23. This is the red brass. The recipe changed slightly compared to before. As for now, it contains 85% of copper and 50% of zinc. This alloy is famous for being tough. It is known as the best copper alloy for resisting corrosion. There is a specific problem called season cracking, where brass crack in a bad weather or stressful environment. Red brass is immune to this. It does not crack easily. In microstructure, just like the first one, this is also a single-phase alpha alloy. Because the structure is so uniform and consistent, there are no weak spots for rust or crack to start. This makes it perfect choice for plumbing pipes, valves, and things that need to survive underwater or outdoor for a long time. As for conclusion, the jewelry bronze is all about beauty. It used the soft alpha structure to look like gold, and for the red brass, it's all about durability. It used strong alpha structure to stop crack and rust. Both are in the alpha phase, but we use them for completely different jobs. Thank you.
Hello, good morning everyone. My name is Muhammad Hazmi. My metric number SL241658EMMHF01. So today I want to present about low brass 80% copper and 20% zinc. So this slide present low brass which consists of 80% copper and 20% zinc is classified as a solid solution alloy and exists entirely in the alpha phase. During solidification, low brass solidified over a narrow temperature range of about 30 degrees Celsius rather than a single temperature. Within the range, a meshy zone forms where the liquid and the solid alpha phase coexist. The cooling curve shows the solidification beginning at the liquidus temperature of approximately 1000 degrees Celsius and completing at the solidus temperature of around 1970 degrees Celsius. In the meshy zone, the cooling rate slows due to the release of the latent heat. At 700 degrees Celsius, the solubility of the zinc in the alpha branch is about 37%, which is much higher than the 20% zinc in the alloy. Therefore, low brass remain fully within the single-phase alpha region. The microstructure shows a quartz alpha grain and annealing twin may be observed especially after the heat treatment. This, this stable alpha structure gives a low brass it a good ductility and corrosion resistant. And now, this slide shows a cartridge brass which contains 70% copper and 30% zinc. This is classified as a solid solution alloy located near the solubility limit of the zinc alpha brass. During equilibrium cooling, the alloy ideal solidified as 100% alpha paste. However, if a cooling is too rapid, a small amount of metastable beta paste can be formed between dendrite, which can reduce the ductility. From the cooling curve, the solidification starts at the liquidus temperature of about 955 degrees Celsius and it end at the solidus temperature of around 915 degrees Celsius. This gives a wide freezing range of approximately 40 degrees Celsius, which increases the risk of the segregation if cooling is not controlled. At room temperature, assuming proper annealing, the alloy contains 100% alpha paste. The microstructure shows uniform equal grain with prominent annealing twin, indicate that the metal has been worked and recrystallized. The structure gives a cartridge brass it excellent ductility and formability, making it ideal for cartridge case.
Hello, Assalamualaikum. My name is Muhammad Ali Syami bin Harun. My matrix number is XX241684EMMHF01. Today, I will present about deep drawing brush. This slide covers deep drawing brush, which is a composition of 67% copper and 33% zinc, which is classified as a solid solution alloy. Since the zinc content is below the solubility limit of the alpha phase, zinc remains fully dissolved in copper, forming a single-phase structure, single-phase alpha structure. Solidification process. The solidification behavior is very similar to 70-30 brass. As zinc content increases, we approach the maximum solubility of the alpha phase. This alloy solidifies completely as alpha, but careful temperature control is required during hot working to avoid entering the beta phase field. The cooling curve shows typical solid solution behavior, which no isothermal arrest. Solidification occurs over a temperature range, which a liquidus at approximately at 940 degrees Celsius and solidus at around 905 degrees Celsius. Phase calculation at 400 degrees Celsius. At 400 degrees Celsius, zinc content at 33% is well below the solubility limit of approximately 39%, so the alloy exists as 100% alpha phase which no beta phase presents. Microstructure image. The microstructure is indistinguishable from 70-30% brass under optical microscopy. It consists of recrystallized alpha grains with prominent annealing twins, which are characteristic of FCC materials like brass. In summary, 6733 brass is a fully alpha phase alloy with solid solution strengthening, predictable cooling behavior, and recrystallized microstructure suitable for extensive plastic deformation. Next is yellow brass, 65% copper, 35% zinc. This slide shows yellow brass which composition of 65% copper and 35% zinc, which lies very close to the alpha beta phase boundary. It is classified as a saturated solid solution, meaning the zinc content is close to the maximum solubility limit of zinc in the alpha phase. Solidification process. Although the alloy solidifies primarily as alpha, its proximity to the alpha plus beta regions means the microsegregation during solidification can locally increase zinc concentration, leading to beta phase formation in certain regions. Cooling curve sketch. The cooling curve shows a relatively narrow phasing range, with liquids around 930 degrees Celsius and solids near 895 degrees Celsius. While it approaches the peritectic temperature, it does not undergo an invariant reaction. Phase calculation at 220 degrees Celsius at room temperature, 35% zinc is very close to the solubility limit of the alpha phase, so the alloy is nominally single-phase alpha. Although trace amount of beta phase may remain if the material is not fully annealed. Microstructure image mainly of alpha phase grains which appear lighter. The darker regions at grain boundaries correspond to small amount of beta phase, formed due to local zinc enrichment. Any visible lead particles are discrete and do not participate in the copper-zinc solid solution. The presence of small amount of beta phase is increased strength but reduced ductility compared to deep drawing brass. In summary, 3535 yellow brass lies at the edge of the alpha phase stability, making its final properties highly sensitive to cooling rate and heat treatment.
Good day, everyone. My name is Bibi Shubhashini, daughter of Kumarisan, and my metric number is XF241660EMMHF01. And today I'll be presenting a comparative analysis of two copper zinc alloy, which is basis brass and also Mons metal. Starting with the basis brass 63/37, as shown in the Cooley curve, solidification begins at the liquid's point of approximately 920 degrees Celsius. It transforms from a liquid into a single-phase solid solution, which is known as a alpha phase, because 37% zinc is below the maximum solubility limit at 600 degrees Celsius. Our level rule calculation confirms the alloy is 100% alpha. Looking at the microstructure, you see uniform equax grains, and the FCC structure of the alpha phase makes this alloy extremely ductile. And for the method of improvement, we typically use cold working followed by annealing to refine the grain structure and to prevent the stress corrosion cracking. Its primary application is in part which is requiring deep drawing, such as cartridge cases and electrical components. Now we look at Mons metal 60/40. The 3% increase in zinc changed the solidification entirely, and it starts to solidifying at 905 degrees Celsius into a pure beta phase. As it cools below the solvus line at 770 degrees Celsius, the alpha phase begins to precipitate out, creating a duplex, which is alpha and beta microstructure. The microstructure sketch reveals a needle-like, which is known as a Whitman-Stanton structure. The dark aqueous beta phase has a BCC structure, which increase strength but reduce ductility at room temperature. By applying the level rule at 600 degrees Celsius, we calculated a phase distribution of 83% of alpha and 70% of beta. So, to improve this material, we utilized hot working. The beta phase becomes very plastic at a high temperature and also allowing us to forge or extrude complex shapes that will be impossible with single phase brass. And common application included, which is architectural panels and marine hardware due to its excellent wear resistance.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Atika binti Muhammad Saimi. Matric number SX242218 EMMH F01. My slide is regarding for free machining brass 57%, 40% and 3%. Free machining brass. Now, let's look at free machining brass, which is a 57%, 40%, 3% alloy. The secret sauce here is the 3% lead. Unlike copper and zinc, lead doesn't mix into the crystal structure, as you can see on the cooling curve. While the brass starts solidifying at high temperature, we see a tiny thermal arrest at 327 Celsius. This is where the liquid lead droplet finally freeze into the discrete globulus. If you look at the microstructure diagram, those small dark spots are the lead particle. In a machine shop, these are lifesavers. They act as internal lubricant and cause chip to break off into small pieces rather than long coil. This allows for much higher machining speed and longer to life. White brass. Moving on to white brass, we have an equal 50-50 split of copper and zinc. This is a very different piece compared to the alpha-rich brass we usually see. As shown, as shown in the cooling curve, it solidified relatively quickly between 880 Celsius and 850 Celsius into a nearly pure beta phase. The unique thing here is the ordering reaction. As it cools further, the atoms arrange themselves into a very specific order BCC lattice. Looking at the microstructure, you'll see large distinct beta grains because it's a BCC structure. You won't see the annealing twins found in the softer brasses. While this material is quite hard, it is also brittle. If we were to increase the zinc content even slightly beyond 50%, we would start seeing gamma phase precipitates, which can make the metal even more brittle and prone to cracking.